Bismillahirrahmanirrahim. So before this, in lecture 18, 19, 20, and 21, I've explained different versions of principle of mathematical induction, and I've also explained how to how to use the summation notation. Now we will try to do some examples and bit exercises. Okay. So we start with this example. So we have a sequence of integers u0, u1, u2, un, and so on, such that the first term and the second term are 2 and 3. And we can write the nth plus 1th term of this sequence is 3un minus 2 into un minus 1. Okay, perfect. And this is for all n greater than or equal to 1. We call such a equation a recurrence relation for the sequence. The question is, can we find a formula for un? Can we find a formula for the nth term? Okay. Now, solution. Using the equation with n is equals to 1, for n is 1, we get u2 is 3 u1 minus 2 u0, which is 5 if we just put these two values. Okay, right. And likewise, u3 is, which is going to be for n is equals to 2. So n is 2, u3 is 9, n is 3, u4 is 17. Remember, this equation starts with un plus 1. That's why for n3 it is u4 and for n2 it is u3. Okay. Then for u5, which is n is equals to 4, u5 is 33, and then u6 is 65 for n is 5. Okay. Can you see a pattern? Is there any obvious pattern? Yes. A reasonable case seems to be that un is 2 power n plus 1. Okay, so let us try to prove by strong induction that un is 2 power n plus 1. So we can say we have this statement. We have to prove this. And by a strong induction, means by principle of strong induction, we say that P of 0 is true, which means is u0 is just 2, power 0 plus 1 is 2. And suppose P of 1, P of 2, up to P of n are all true, then un is 2 power n plus 1 and un minus 1 is 2 power n minus 1 plus 1. Hence, from the recurrence relation, we get that un plus 1 is 3 into 2 power n plus 1 minus 2 into 2 power n minus 1 plus 1. If you solve this, you will get 3 into 2 power n minus 2 power n plus 1, which is nothing but 2 power n plus 1 plus 1, which shows that p of n plus 1 is true. Therefore, un is 2 power n plus 1 for all n by strong induction. Perfect. This is very interesting. Okay. Now we can say, we can do another exercise which says that prove the following statements by induction. Prove the following statements by induction. So A, for all integers n, for all integers, so we can also write n greater than or equal to 0. This means n is an integer, and for all n, the number 5 power 2n minus 3 power n is a multiple of 11. Let's give the solution. To solve this, what we can say that let's try the solution again with the same let p of n be the statement that 5 power 2n minus 3 power n is a multiple, is divisible by 11. Divisible by 11. Then p of 0 is true, is 5 power sorry. Then suppose p of n is true, so 5 power 2n minus 3 power n is nothing but 11 into k for some k in integers. Now 5 power 2n plus 1 minus 3 power n plus 1 can be written as 25 into 5 power 2n minus 3 into 3 power n, and this can be written as 22 into 5 power 2n plus 3 to 5 power 2n minus 3 power n. and this is nothing but 22 into 5 power 2n plus 33k, which is divisible by 11. So you can write which is divisible by 11. Hence, P of n implies P of n plus 1. And therefore, P of n is true. B. Number B says, for all integers n greater than 0, not 0, 1, the integer integer 2 power 4 and minus 1 ends with an 8. Solution. Let's say P of n is a statement which is that 2 power 4 and minus 1 ends with an 8. That means 2 power 4 and minus 1 is 10k plus 8 for some k in integer. Now clearly P of 1 is true because 2 power 4 minus 1 is 2 power 3, which is 8. Now assume P of n is true. Say 2 power 4 and minus 1 is 10k plus 8. Then 2 power 4 into n plus 1 minus 1 is 2 power 4 into 2 power 4 and minus 1, which is nothing but 16 into 10k plus 8. And this can be written as 160k plus 128, which ends with an 8. And which ends with an 8. Hence, P of n implies P of n plus 1. And then P of n is true. Now, C, if x is greater than or equal to 2, a real number, and n is greater than or equal to 1 is an integer, then x power n greater than or equal to nx. Solution. We say let x is greater than or equal to 2, then P of n is in a statement that x power n is greater than or equal to nx. Then P of 1 says that x is greater than or equal to x, which is true. Then assume P of n and multiplying both sides by x, we have x power n plus 1 is greater than or equal to n x square. Now observe that nx square is greater than or equal to n plus 1x, since this is equivalent to x greater than or equal to n plus 1 over n, which is true, is x is greater than or equal to 2. Hence, x power n plus 1 is greater than or equal to nx square, which is greater than or equal to n plus 1 into x. So we have shown that P of n implies P of n plus 1. P of n implies P of n plus 1. Example says that the Fibonacci sequence f1, f2, fn such that f1 is 1, f2 is 1, and fn plus 1 is fn plus fn minus 1 for all n greater than or equal to 1, prove by a strong induction that for all n, the nth term of this sequence is nothing but 1 over under root 5 alpha power n minus beta power n, where alpha is 1 plus under root 5 over 2 and beta is 1 minus under root 5 over 2. Okay, perfect. So let P of n be the statement. Say that f of n is 1 over under root 5 alpha power n minus beta power n. Since 1 over under root 5 into alpha minus beta is 1, which is the first term, so P of 1 is true. Now assume P of 1 to P of n are all true. Then we have f of n plus 1. Fn plus 1 is fn plus fn minus 1. That is 1 over under root 5 alpha power n minus beta power n plus 1 over under root 5 alpha power n minus 1 minus beta power n minus 1. And this can further be written as 1 over under root 5 is common. So we can write alpha power n minus 1 into alpha plus 1 minus beta power n minus 1 into beta plus 1, right? Now, alpha plus beta is 1 and alpha into beta is minus 1 from above. So alpha comma beta are roots of the quadratic equation. Roots of x square minus x minus 1 is 0. So alpha square is alpha plus 1. Beta square is beta plus 1. It follows that fn plus 1 is nothing but 1 over under root 5 alpha power n plus 1 minus beta power n plus 1, which is p of n plus 1. Hence, the result follows by the principle of mathematical induction. Thank you so much. See you in the next chapter.